Alrighty, 4.4. 4.4 notes properties of matrices. So, we've got properties of matrices here. Let's talk a little bit more about what a matrix is, right? So I told you we were going to be working with these a little bit more. We just saw in the last section that they can help us solve systems, which is still very, very important. But they actually do a lot more besides that. So let's talk about what they really are. A matrix, in a most general sense, can look like this. Now, I know this is kind of crazy, but it just basically shows you that it could be any size, right? It can be any size. It can have any number of numbers, right? Any number of entries. So there would be m rows here, right? So m rows goes all the way up to m, as you can see, and it goes all the way out to n. So it always has m rows and n columns. Now that's just to say there's a generic number that you could have. More oftentimes you'll see stuff like this, where it's a 2 by 2, 2 rows, 2 columns. You might see something like a 1 by 3, things like that. So you can have matrices of any size. We call these things entries. So these guys are entries. An entry is a number within a matrix, right? Now this one, the specific subscript, tells you that it's in the first row, first column. It does not tell you it's in the 11th spot, okay? So those are actually two different numbers there. 1, 1, if you want to think about it that way, is the very first row, first column. Whereas over here, this one would be first row, third column, and we always go row by column. I'm going to write that a little better. Row by columns. Every single time when we're naming them, when we're multiplying them, it's always row by columns, rows by columns. Rows, rows, rows are first. Excuse me. Okay, now some matrices can be equivalent, but matrices are not only equivalent if they are the same size, they have to have all the exact same entries and the same entries in the same place. So these two we can tell are definitely equivalent, while these two not so much, right? They may have the same numbers, they may be the same size, but it's not in the same order. So order really matters when it comes to a matrix. Otherwise, when we're solving these, we'd end up getting different numbers, right? So let's see if we can kind of work with this idea that they must be exactly the same to figure out some of these missing variables. So let's take a look at example 1.1. If possible, state the values for what that would make the statement true. So if these two matrices were actually true, what would we say x was? It's not really a trick question. X would correspond to the same thing as first row, first column, right? So x is in first row, first column in the second matrix. Therefore, it has to match the first row, first column in the first matrix. So x is equal to 2. Similarly, y must match what's in the first row, second column for the first matrix. So that would be 1, right? So y is equal to 1. And then we can do the same thing on the bottom. So if P is to match the second matrix, that's first row, second column, right? Sorry, second row, first column. This is entry 2, 1, right? So P would have to be equal to what? That's right, it'd have to be the same thing as over there, or -1. And then last but not least, Q would be in second row, second column, and so it has to match the 0. Q would be equal to 0. Alrighty. So we can see that in order to match, they must match entry by entry. This is what we call entry by entry. Alright. What about this one down here? Is it possible to determine which ones match? Not really, right? Because this one only has 2 entries, and this one has 3. So this can never possibly match entry by entry, and so these two will never be equivalent. It will never be equivalent, okay? So it's got to match not only in size, but entry by entry. It's got to match. All right, cool. We can also add matrices, right? And that's, again, they have to match. They don't have to match entry by entry, but they have to at least match in size, right? So we can add and subtract matrices just like we would add and subtract numbers or equations even. We could do that. But we're going to add and subtract these matrices. First, we have to decide if we can. What do you think in this first one? Can we add these two matrices? Are they the exact same size? They are indeed, right? So they are the same size. They're both 2 by 2s, 2 rows. We would write that 2 by 2 plus a 2 by 2. And as long as they have the same rows and columns, then we can add them entry by entry. Everything with matrices is always done entry by entry. So let's go ahead and do that. We add these two together. We're going to end up with another 2 by 2 matrix. And let's go ahead and do that. Now we got to be super careful because we want to make sure we don't drop negatives or anything like that. But let's go entry by entry. So this first row, first column, first row, first column, 5 plus negative 4 is going to end up being a 1. This next column, first row, second column, 6 plus negative 6, or sorry, negative 6 plus 6 is going to be a 0. This third entry, this first or second row, first column, and second row, first column, 8 plus 8 is going to be 16. And then this last one is second row, second column, plus second row, second column, 9 plus negative 3, or 9 minus 3 is 6. And we end up with this new matrix of 1, 0, 16, 6. Awesome. What about this next matrix? Do you think it's possible to add that? I hope you guys said no, because what on earth would you go how on earth would you go entry by entry? Here's the first row, first column. Here's the first row, first column. Okay, maybe you could get away with that. But then you're looking for the second row, first column, and you're like, okay, it's not there. Okay, I don't know what to do now. Maybe I'll add it with this one, and then who gets added with the one, question marks, and frustrated faces all over the place, right? So we can't add these. This is not possible, right? Not possible. So if they're not exactly the same size, a 2 by 2, this one is in fact a 2 row by 1 column and a 1 row by 3 column. Those two are not corresponding. They don't match at all, right? So we can't do that. So 2 by 1 and 1 by 3. All right, what about this third one? We're going to subtract it this time. Do you think it's possible? Yes, this one would be possible because they are both 1 row by 3 columns and 1 row by 3 columns, right? They're not 3 by 1s. They're 1 by 3s. 1 row by 3 columns, right? 1 row by 1, 2, 3 columns. So we'll just add entry by entry, and we end up with another 1 by 3. We got to be careful though because we're subtracting this time, so we got to make sure we subtract in every instance. We'll do this first. First row, first column. 8 minus 3 is 5. And then we've got, let's not use blue, purple. First row, second column. 6 minus 5 is 1. And then first row, third column. Negative 4 minus negative 8 or negative 4 plus 8 would give us a positive 4. And we end up with our new matrix, right? Cool. If you have any questions, make sure you pause the video so that you can get those question answers because it only gets a little more complicated from here. Alright, so let's talk about something called the zero matrix. Sounds super complicated, isn't? It's a matrix of all zeros. It's pretty much on the nose. It's any size you want, 1 by 2, 3 by 5, 16 by 47. As long as you have all zeros in the matrix, you end up with the zero matrix, right? And woo, that's super complicated. So yeah, basically it's a matrix of all zero. When you want to find, or when you get the zero matrix, when you add two matrices together and you get the zero matrix, we call those two matrices the additive inverses of each other. So they're inverses. We have to be careful because we're talking about the additive inverses. Excuse me. The additive inverses will give you the zero matrices. So we take a look down here. If we call this first matrix A, right? We call this first one A. Sometimes we name them with letters, right? Talk about same thing with functions. Name a function F, name a matrix A. That's usually what we do. And we add it to this matrix, the matrix additive inverse. Notice you've got this A to the negative 1. That's an A inverse, okay? So that's the notation we see. Well, notice that every entry is just kind of opposite. And when you add the two together, you end up with a zero matrix. So if you wanted to find the additive inverse of a matrix, you just have to think, how would I end up with the zero matrix when I add it to this original matrix. So let's try that out. I've got this matrix. I'll call it matrix B. I need to find B inverse. I need to find B inverse, the additive inverse of this matrix. In other words, I need to find a matrix so that when I add it to B, B plus B inverse, I end up with a matrix of all zeros, right? So what matrix would do that? What matrix here? What do I need to add to -3, to get 0? Well, I just told you it needs to be a 3, right? 3. What do I need to add to 6 to get to 0? I need to add a -6. What do I need to add to 9 to get to 0? I need to add a -9. And what do I need to add to -5? I need to add a +5. And so there is our matrix inverse, right? You just switch the sign on each of them so that when they add together, they give you that 0 matrix. Alrighty. Moving quite along, because really that's not that hard. So that's addition and subtraction with matrices, and really what it comes down to is you must have the same sizes and they must go entry by entry every single time. Next we're going to talk about something called multiplication by a scalar, and it's very important that you remember this is not multiplication of matrix times matrix, okay? This is different. When we want to multiply a real number into a matrix, just a number, not another matrix, not a function, not anything else, but just a number, it's called a scalar, okay? It's a scalar. So a scalar matrix multiplies the entire matrix by 5, and it's just straight distribution property. If you have 5 times a matrix, you just multiply entry by entry. Distribute the 5 into everybody, okay? So that ends up being 5 times 2, -3 times 5, 0 times 5, and 4 times 5. So I'm just multiplying each entry by 5, and I end up with the new matrix of 10, -15, 0, and 20. That's going to be our new matrix, our scalar multiplication. Sometimes you'll see these things like if you have this matrix here of 2, -3, 0, and 4, and this matrix is called C, we'll call it C, then go ahead and find me 5C, right? And that's the same thing as multiplying 5 to the matrix. You just end up with this guy being 5C. Alright, cool. Pause right here. I know I went kind of fast, but I figured these were a lot easier than the sections we talked about before, so I figured this was mostly review and you can catch on, not review, but it's very, very similar to what you would do with equations. But if you have any questions at all, please pause and get your questions answered. So we're going to go on to next. It's just a little bit more complicated.